nice to be cold. Aiden's like, whatever. But I like it. I like being able to wear a sweater instead of a t-shirt, you know? Like we get so hot out here and it's expensive. Being hot is expensive. Like if you don't want to be hot anymore, air conditioning's expensive. This is all in my video, so I should probably stop talking about it, but I can't until I finish the thought. Being cold doesn't cost anything, right? I just throw on some more clothes. I've got plenty of sweaters. Costs a lot less to be cozy when it's cold. And then around here too, a lot of the houses have wood burning fireplaces. So when I get out of my car in the morning and I smell that, it's just so nice. Such a nice thing. So we are back talking about systems of equations, right? Which is more than one equation that have common solutions, right? And we are trying to find those common solutions. Systems equations. It would be systems of equations, not just systems equations, because that's stupid to say. And today we're specifically talking about solving using substitution. We will move into things called like elimination and other methods as we move on, but today is just the basics, and that is substitution. And the way substitution works is by understanding what equal means, right? If let's see, if I have something that says y equals 4, right? If I told you that y equals 4, and I also told you that y equals s, right? Or X or P or whatever, right? That's the same thing as saying that 4 equals S, is it not? Like if Y equals 4 and Y equals S, then clearly 4 equals S. Does that make some sense to you? Because that's the kind of logic we're going to use. And so if you can understand things like that, then yeah, but Nathan, that firewood smells so good. People are going to be like, what is she talking about on that video? But I just saw it. So hopefully you guys can kind of follow along with that. I'm going to start here by writing down some steps for solving by substitution, and then we will get into actual problem solving. And let's just go ahead and erase these before we. Dang it. I don't like the eraser on this whiteboard because it doesn't always like, see how many times I had to do it before it stayed on for me? So number one, when we're solving using substitution, you want to solve one of the equations for x or y. Right? What does that mean? It means we're isolating a variable, right? We're either going to isolate x or we're going to isolate y. Doesn't matter which one. Sometimes one will be easier than the other. That's the one you're going to solve for. Number two, we're going to substitute resulting equation for either x or y, depending on whatever we solve for. From step one into the other for that variable, I guess. I'm trying to think of how to say it. Into other equation for, I'll call it chosen variable, whatever we solved for. This will make more sense when we are doing it. Number 3, solve for the remaining variable. Sometimes I think I should use text for this part and just type it in, and then it would be far more legible. Substitute answer from step 3. From step 3 into original equation. So let's look at what that looks like in reality. That is the worst spelling of original. It's so ugly. It looks like my A is G. All right. And that'll find us our other solution. Let's look at what that looks like in practicality, because right now it's just a bunch of words. None of them make any sense. I understand that, but they're good to have after you go back and start doing it yourself so you could see what happened along each step. So we are going to start with some examples. Let me bring this down in case people are still writing, if anyone is actually even writing. We're going to start with our first example because, well, it'd be stupid to start with our fourth example. If I have y equals negative 7x minus 1, and I have y equals x minus 9. Now, our steps say that we're going to solve one of the equations for x or y. We're going to isolate the variable. But in this case, both of them are already solved for y. We don't need to isolate the variable because both equations are already solved for y. Both of them are already isolated. But like I'd said before, is if I had y equals 4 and y equals s, I could write 4 equals s, right? So here, if I look at these two equations, right, they're both already solved for y. So I can take whatever this y equals, right, and whatever this y equals, and I can set them equal to each other, right? I could rewrite this as minus 7x minus 1 equals x minus 9. And I can do that because they're both y equals, right? And what that's going to do is now I can solve this equation that I wrote right here for x. There's only one variable in there, right? We don't have a y variable anymore. So we can find a numerical value for x, and then we can plug it into those other equations and figure out what y is. So we do that by undoing what's happening to x. I like to have all of my x's on one side, so I'm going to start by subtracting this x from both sides, and I'm going to have negative 8x. Oh, help if I wrote the x. Minus 1 equals negative 9. And then I'm just going to add this 1. I'm going to start making moves until all I have left is x on one side. Negative 9 plus 1 is negative 8. The only thing I have left going on here is I have that negative 8 being multiplied to x. So I'm going to divide both sides because that is the opposite of multiplication by negative 8. And I'm going to get that x equals negative 8 over negative 8 is just positive 1. Anything over itself equals 1, right? So now we know that the common solution for both of these equations is x equals 1. And to find what y is, all I have to do is plug it into one of these equations, right? So I go, okay, well, I have y equals x minus 9, but we know that x equals 1. So that is 1 minus 9, which is negative 8. So our point value, our solution, is x equals 1 and y equals negative 8. And that is the true solution for both of these equations. And we can check it if we want to, right? Like we know the first one, we already plugged it in, but if I plugged it into the second equation, right, I would go, okay, well, if I had minus 7 times 1, that's what x is, minus 1, I should still get negative 8 as a solution. Negative 7 times 1 is negative 7, minus 1 is negative 8. And you can see that the y is the same for both equations, right? We're still getting 1 and negative 8 as a true solution to each of those equations. And so we know we're right here. If we wanted to go through the process of checking it, we could do that, right? We could just plug those in and see if it's true. For both, right? It has to be true for both equations. So that's kind of how it works, but we're not always going to have all of these problems lined up for us, right? We're not always going to be given like two that are set as y equals, right? Which kind of lessens the blow. Sometimes we're going to have to do a little bit more work. So actually almost all the time, we're going to have to do a little bit more work. That's how math is. Like it just won't go easily for us, right? It makes us work for it. If we look at our next example, let's see, where do I want to go with this? Because I have a couple. Let's start here and then if I have y equals minus 5x plus 30, and I have 7x plus 3y equals 42. Now, one of these equations is already solved for y, right? Right here, we have a y equals something. So I really don't have to do anything as far as like isolating one of the problems. What I know is that because y equals this, right, this minus 5x plus 30, it means that I can take what it equals and plug it right in here for y. Does that make a little bit of sense? Oh, I can't see a single face anymore, so I can't see a head like nodding. So I'm going to assume that you're all following along right now. So I can take this 7x plus 3y problem, and where the y is, I'm going to plug in negative 5x plus 30, right? Equals what? 42? And now I can solve this problem for x because I don't have any more y variables in the equation. So I'm going to start by doing my distribution. So I'm going to leave this 7x, and I'm going to go 3 times 5x. Well, that's negative 5x. That's, oops. Oh, how do I make that go away? Like that. That would be negative 15x. Right? And then I have 3 times 30. Well, that's 90. So we're going to go plus 90 equals 42. And now we're going to start combining our like terms, and we're going to move our numbers to one side and our x's to the other. 7x minus 15x is negative 8x plus 90 equals 42. Then next we are going to start undoing all of the stuff, right? We've got 1x on both sides now. So I'm going to start by subtracting 90 from both sides. I have no idea off the top of my head what that equals. Negative 48. So I get negative 8x equals negative 48. And the only thing I have left going on to that x now is this negative 8 that's being multiplied to it. So I'm going to go ahead and divide both sides by negative 8 so that all I have left on this side is x equals negative 48 divided by 8 is 6. So we have found the first value of our solution, right? We know the x value is going to be 6. We don't yet know what the y value is going to be. But it doesn't matter because all I have to do is take that x value now and plug it into one of the equations. So here I've got y equals negative 5x, and we know that x equals 6 plus 30. So to find out what our y would be, we're just going to do the math on this, right? Negative 5 times 6 is negative 30 plus 30. Well, that just equals 0. So that is saying that our y value would be 0, right? This would be our solution. If we wanted to prove it, we can plug it into the other equation as well and find out if it's true. But I'm not requiring that you go back and check all of these, right? What have we found out? We found out that our x is 6 and our y equals 0. And that is going to be true for both of those equations. That is going to be the point where these two lines intersect on a graph, right? It's where they have a common solution. Does that make some sense? All right. So let's look at least one more. I don't know if I need to do a bunch more, but I should definitely do one more where none of them are solved for y or x, and that we have to do that first step. If I have 6x minus 5y equals negative 28, and I have 7x plus y equals 22. When we're doing substitution and you see a problem where one of the variables, like variables, if you remember, like our x or y, whatever those substitutes are, if one of them doesn't have a number in it, solve for that one, right? Like I would look at these two equations, and when I want to isolate the variable, I can look at this and I go, well, this one looks pretty easy to isolate, right? Because there's nothing on that y. I could definitely get that to be a y equals something fairly easily, right? Because the only thing I have to do to make that y equals, right, is to move over this 7x, right? So that's the problem I'm going to work with because there is nothing in front of that y. I'm always going to look for a problem like that that's really easy to get by itself because I'm lazy and I don't want to do extra work if I don't have to, right? So I'm going to start by subtracting 7x from both sides so that I get y equals minus 7x plus 22, right? So now I can take this and I can plug it in for x on this equation. I cannot do it into the same equation I used to isolate. I can't plug it back in there. I'm not going to get anything from that. I have to do it in the other equation. So I have 6x minus 5y, but I know that y equals negative 7x plus 22 equals negative 28. And now I can solve and figure out what my x is. So I've got 6x minus 5 times 7 is plus 35x plus, shoot, man, I don't know what 5 times 22 is. 110? Is it 110? It's 110. Negative 110, right? Because we have a negative times a positive equals negative 28. And now I can just start solving for x. I can start 6x plus 35x is 41x minus 110 equals negative 28. I can add 110 to both sides plus 110 plus 110, and I would get 41x equals, I'm counting on my fingers, 82. Positive, right? Because minus 28 plus 110 is going to give us a positive solution. And then conveniently, when I divide out this 41, 41 conveniently divides evenly into 82, and I would just get x equals 2. So we went through all of those crazy big numbers to start, but what we wound up with so far is that our x value, oops, yeah, I'll do it like this. I'll make it look like I meant to do that. Our x value so far is 2, and we still need to find out what our y value is. But our y value is really easy because now I can just plug it into either one of those equations, right, and find out what it is. So I'm going to start with this one. I'm going to go y equals negative 7 times x. Well, x is just 2 plus 22. And I'm going to get negative 14 plus 22, which is y equals 8. And so we know that our y value is 8. And if I plugged those x and y's into either one of our original equations, our answers are going to be true. 6x minus 5y, when x is 2 and y is 8, is going to give us negative 28. 7x plus y equals 22 is going to be true when I plug in 2 for x and 8 for y every single time, right? It is our common solution. So one more because, well, I like to torture you. And then I will be done with you all. Well, until next week, not forever. Last example. If I have 2y equals 6x plus 10, and I have 3x minus y equals 5. I'm going to look at this first problem right here. They're both pretty easy to solve for something, but look at this one. All I have to do is divide everything by 2, right? So I'm going to go, okay, I'm going to use this one. I'm going to go 2y equals 6x plus 10, and I'm just going to divide everything by 2. And once I do that, I wind up with my y equals, well, 6x divided by 2 is 3x. 10 divided by 2 is plus 5. And looking at that, I have an equation here that's really similar to this one, is it not? Like, I think they might be the same. Does that make any sense to you? So if I look at this, if I have 3x minus y equals 5, right? And I wanted to solve this one for y as well, I'm going to subtract 3x from both sides, right? And I'm going to get minus y equals negative 3x plus 5. And then I would have to divide this whole thing or multiply it times negative 1, right? So I'd have to go negative 1, negative 1, negative 1, and I would get y equals positive 3x minus 5, which is the same as that, is it not? No, it's not. Positive 3x minus 5. Ah. So these aren't exactly the same, right? I have 3x minus 5 equals 3x plus 5. So if I subtract out the 3x on this side, I get minus 5 equals 5. Is that true? Is that a true statement? Can minus 5 ever be equal to 5? No, it can't, right? When we have a solution like this, we've done this before, we've been here before, when we were working on solving equations, right? When we first started working on it, and we'd come to these problems where we would have two things that can't equal each other, right? Negative 5 plus equals can't equal 5. Never can that be true. We would just say there is no solution, right? We write it like that. We could say no solution. Any way you wanted to put that, you would show it, but you have to show me why there's no solution. Do you have any no solution problems on your worksheet? I don't know. If it was true, like if we wound up with something like this and all our variables went out, but the statement was true, say it was 5 equals 5, that would mean the solution is all real numbers, right? But in this case, doesn't equal each other, so our solution is no solution. I think that'll work pretty good for now. I don't think I need to show you several more examples. I might show you an example where one is not easy to substitute out, but I don't believe you have any like that in your worksheet, and I would rather use elimination for problems like that. But I will go through your worksheet and make sure there's nothing more complicated than what we've done. And if there are, I will make a little video and I will show you guys how to solve problems like that on like a little separate video so that if you guys get stuck, you have something to go back to. Let me stop the sharing.